All right, so yesterday we finished up talking about electrophilic aromatic substitution when you've got a aromatic molecule with multiple substituents coming off of it. So in the first example, we identified the methyl group as being an ortho-para-director because it's electron donating. The para position was blocked, therefore we just had the two orange arrows in the top right and left-hand corners. And we know that nitro groups are electron withdrawing, so those would be meta-directors relative to the nitro group, and that's where we have the green arrows pointed. So we were able to predict yesterday that this would be our major product, not the one crossed out. And then we said if you run into these tiebreaker situations or situations where there's inconsistent arrows, then you immediately go to your strongest activator. That will be the one that will win out. And then after that, I said if there's still a tie, then the most accessible carbon will win. So I kind of want to get back to point 3 and take a look at that. Point 3 is assessing sterics, meaning how accessible a site is for electrophilic aromatic substitution. So let's take a look at steric effects in more detail. And specifically, we're going to look at this problem. How do you pick ortho versus para? We know that if we have an electron donating group, it's going to be an ortho-para director, but which one's going to win, or are we going to get both? Are we going to get complicated mixtures? It's not always clear. So let's take a look at a simple starting material. We'll look at toluene. Like we saw on the previous page, that methyl group, this one right here, is going to favor the ortho positions right there and there, along with the para position down there. So if we were to treat this with elemental bromine and iron tribromide and assume we're only monobrominating it, we could have one product where the substitution occurs at the ortho position, or we could have one where it occurs at the para position. All right, so my question for you is which one do you think will be major and why? And then talk about it with your neighbor. All right, raise your hand if you think the para substituted will be major. All right, does anybody want to explain the reasoning for why they think para would be major? So somebody just blurted it out, sterics, all right? So that's a reasonable explanation, right? If we look at this one over here, you could say, well, sterically, that bromine could brush up against that methyl group. However, a methyl group, in terms of steric bulkiness, really isn't that big. Did anybody pick the ortho substituted one? Yeah?
I picked ortho because it has two ortho positions that can attack.
Okay, so you picked ortho because there are two positions that could act as the nucleophile rather than one with the para substitution. So you're saying statistically that's more likely?
Yeah.
So I think we've got a really good argument going on, right? We've got one argument about statistics saying that we've got twice as many reactive orthocytes than we do para, and then the other one is invoking sterics. In this case, statistics wins. So this one's going to be our major product due to stats. That basically just means we have twice as many ortho positions. The reality is you will get some of that para substitution as well. It's just the statistical mixture, and we're going to get more of the ortho substitution. All right, so let's consider this one. And let's say we've got iron tribromide. Again, we know that any alkyl group is going to be an ortho-para director. So we could end up with the bromine on the ortho position, or we could end up with that bromine off of the para position. All right, which one do you think is going to be major for this situation? Para. So this one is definitely going to favor para because in this situation, we are going to run into a considerable amount of steric clash between the bromine and the tert-butyl group. A tert-butyl group is massive compared to a methyl group. So this would be a major product on the right. due to sterics. In general, anything larger than a methyl group will favor the pair substitution pattern due to sterics, but anything that's a methyl group or smaller tends to favor ortho due to statistical probability. So let's make a note of that. So methyl group or smaller tends to favor para. Or sorry, ortho. Holy cow. Due to stats. And then we can reiterate that large groups favor para substitution. Due to sterics. Yep.
So if you overshoot, is it going to go, like if it's attached to a para, you overshoot, is it going to attach to the other para or the other ortho, or is it going to go para? Like if you attach two profiles.
Okay, so let's consider that, right? I think I understand what you're asking. We'll write it out so everybody can understand. All right. So are you referring to toluene or the? Okay. So let's say we've got this one, and we react this with elemental bromine and iron tribromide once, right? So monobrominate this. We know that the ortho position statistically is going to be favored, although we will observe some of that para substitution. That will be our minor product. All right. Now we're running into a unique situation, right? So the unique situation here is we have more than one directing group. So over here, I'd say, all right, this methyl group favors ortho and para. What about the bromine? Ortho and para as well. Even though that's a deactivator, it favors ortho para. So now we're running into this inconsistency. So what do you think will be favored now? The stronger activator will win out. Which is the stronger activator, the methyl group or the bromine? Methyl group. Okay, so that means that the methyl group is going to be favored. In this case, do we get any statistical benefit for hitting that ortho position? No. So in this one, there's no statistical benefit for the ortho position. So really, this position down here will be favored. So we can go ahead and predict that our final product for this reaction, if we were to do this reaction twice, would look something like this. Does that make more sense? Yeah. That's a good question. So it kind of ties in a lot of those tie-breaking rules that we've been looking at. All right. So now we're going to look at some more challenging situations, because everybody likes a challenge. We're going to look at the use of blocking groups. All right, so let's say I've got tert-butylbenzene, and I absolutely insist on getting my ortho-brominated product. We can't just toss in elemental bromine and iron tribromide, right? Because we just went over the fact that sterically it would favor the para substitution. So we've got to find a workaround. We can't do this in one shot. All right, so then the question is, well, what the heck can we use as a workaround? We've got to have some sort of potential blocking group in order to prevent attack at that para position. What can we use as a removable blocking group? Who remembers? Yeah, so it had sulfur in it. You remember the sulfonation reaction? Okay. So what we could do is we could treat this with fuming sulfuric acid. If you remember, that's sulfuric acid with SO3 added, the sulfur trioxide. We know that this group right here is going to favor ortho and para. However, we know sterically those ortho positions are a lot less accessible than para. So our major product for this one will be para substitution. All right, so now if we look at it, we've got competing groups in solution. We still have this alkyl group, which is going to favor the ortho positions, but now the para position is essentially blocked. And then down here we've got our sulfonic acid group. Is that an ortho-para or a meta-director? So are we going to dump electron density into the ring through resonance or pull it out? Pull it out, right? So this would be a meta-director. So meta to that group would be right here and right here, which means we've got a pretty good clue that it's got to be one of these carbons. Does it matter which one we pick? Nope, they're symmetric, so it doesn't matter at all. So now we can go ahead and brominate that position. We still have our blocking group on, but that's okay. Does anybody remember how we can go about removing this blocking group?
Water.
Not just water. What's that? Not zinc and water. Dilute sulfuric acid. So it's kind of weird, but what we do is we flood it with dilute H2SO4. Yeah, but that's a good point. So in this first step, we had H2SO4, but after the second step, we didn't. So we're going to reintroduce the sulfuric acid, add some water in, and make sure that we can pop this off. So if you remember, this will remove that blocking group. So some of these get pretty fancy where you have to do a considerable amount of planning in order to prevent reactions at sites where you don't want them to react. Does that make sense? All right. So let's take a look at everything we've covered so far before we move into our next reactions. All right, so if you remember at the end of the chapter in your Klein textbook, they have these really nice summary sheets. This top portion, meaning this portion right here, are all of the reactions that we've covered in our first, 3 days of Organic Chemistry 3? So we're going at a pretty decent clip. All of these are electrophilic aromatic substitution. But really, a lot of these reactions are pretty similar, right? We're trying to make a really strong electrophile, we make a sigma complex, and then we restore aromaticity. So really not too bad. And then what we'll cover next are these reactions. A lot of these are just offshoots. In fact, most of these we've covered as well. So for example, this one we said we could convert a nitro group to an aniline by reducing with zinc and or iron and HCl. This one we actually covered last term. That was allylic or benzylic bromination. This one we covered last term. That was oxidation of a benzylic carbon. And then who remembers the name of this one? The Clemmensen reduction. So that was with zinc, mercury, and HCl. So these are offshoots whereby we can derivatize our products made after electrophilic aromatic substitution. All right. And then we also saw that depending on the group that we have, we can have ortho-para-directors or meta-directors. Like we said, if you have an electron withdrawing group, they tend to be meta-directors. If they're electron donating, they're ortho-para, with what exception? Halogens. Halogens are deactivators. They're electron withdrawing groups, but they're ortho-para-directors. The cool thing is, when we do these interconversions, like convert a nitro group to an aniline, we convert what was a meta-director to an ortho-para-director. So we can actually flip-flop the directivity of our substituents by doing some of those simple transformations shown above. All right, there's a handful of tips, though, that I want you to pay attention to anytime you do synthesis. some of these aren't super intuitive, but we have to keep them in mind. The first one is if you have aniline or any sort of amino substituted benzene, and you treat it with nitric acid and sulfuric acid, you end up with goo. Basically, this will rapidly polymerize, and it's not a reaction you can accomplish. So there are tricks around this that we'll cover later, but for right now, we're going to assume we can't really do a heck of a lot with this. All right? Number 2, that's important to remember. Is with Friedel-Crafts reactions like this. What's the problem with this? It was one of the subtle details we went over. Not exactly. So overalkylation can occur on normal aromatic rings with the alkylation reaction. I'll give you a hint. Is this a strong or weak electron withdrawing group? It's a really strong electron withdrawing group. Because of this, you tend to get no reaction. So they won't work with strongly deactivated aromatic rings. So we do have to watch out for that as well. So going off of this, what does that tell you about installing nitro groups? Should you do them early on in your synthesis or later? Later. Yeah, ideally you want to install your electron withdrawing groups later. So that opens up the door for Friedel-Crafts acylation or alkylation, whereas if you put on a nitro group in step 1, you're really limiting your options from that point forward. And along with that, that means you need to pay attention to reaction order, right? So pay attention to which groups you're adding first, second, third, or so on. All right, so what I'm going to do next is give you a practice problem, meaning a target molecule, and ask you how would you go about synthesizing this. And I'll give you a few minutes to work on this. All right. So we're going to start out with benzene, and we can use any other reagents that we want, but our goal with this synthesis is to make the following molecule. So now the question is, well, which group will you add on first, second, third, and so on? What's a good strategy with synthesis in general? Work backwards. All right, just for a little bit of help, for option 1, what would the reagents be that I'd need for that transformation? HNO3 and H2SO4. All right, what about option 2? Just theoretically, what do we need to install bromines? Br2 and FeBr3. All right, and then the last one, what would we need to install the acyl group? Okay.
ALCL3.
And AlCl3. All right, so we got the reagents filled in. The next thing I would do is just take baby steps, right? So let's take a look at this group. Is that electron withdrawing or donating? Withdrawing. Will that be an ortho-para director or a meta director? Meta. So I'll go ahead and point out those meta positions. And then over here I'd say, all right, bromine. Is that an ortho-para or a meta director? Ortho-para, even though it's a deactivator. And then the pair position's blocked. So does this check out? Yep, it checks out. All right, but let's just, for the sake of completion, go to the next one. We already said that this group will be an ortho-para director. The only available ortho positions right there. Or sorry, only available meta position is right there. And then over here we've got our nitro group. What would that do? Meta as well. Only meta position would be right there. Does this reaction look good? No, you could theoretically do it, but you wouldn't get the right product, right? You would get a 1,3,5 substituted benzene. So that wouldn't work because we would get the incorrect regiochemistry. All right, and then the last one. What's the issue? We can't do the Friedel-Crafts reaction due to this nitro group. In addition, we would potentially run into a mixture of products because we already said that this bromine could favor this group over here. And then we also said that the nitro group could favor that position too. So not only will it not work because there's a nitro group on there, but we might end up with a bit of a mixture. So I'd say option 1 is going to be our best approach. Make sense? All right, so now we need to figure out how to make para-bromoacetophenone. All right, so with para-bromoacetophenone, we've got a few options. So I'll just write it out twice just to keep our formatting consistent. One would be maybe we're installing our bromine group in this step. And then the other one would be maybe we're installing that acyl group next. What would the reagent be for the top option? Br2 and FeBr3. And then for the lower one, we need our acid halide and aluminum trichloride. All right, so same idea with the top one. We've got this acyl group. Again, we said that that would be a meta director. Will this reaction work? No. Well, it would work. We just wouldn't get the right regiochemistry, so we could cross that out. All right, and then the next one, we've got bromine, which we know is going to be an ortho or a para director. Yeah, this one would work. People always say, well, what about the halogenation, or sorry, the reactivity at the ortho position? Chances are you would lose some due to that mixture. However, really it's our only option at this point. So we're stuck on this pathway. All right, and then last but not least, how can we make this from benzene? FeBr3. Hopefully everybody can get that one. So a lot of these problems require a significant amount of scratch paper and just kind of mind mapping your way through it. But don't be afraid of finding these dead ends. Sometimes proving a dead end is a dead end is really useful. Just rule that out right off the bat. Does that make sense? All right. So chances are on your first exam, there will be synthesis problems like this, where I say start with benzene and make X, Y, or Z, and you'll have to kind of problem solve your way of getting there. So make sure you do practice the synthesis problems in the book. Some of them look really easy, and then you start working on them, and you're like, oh no, these are kind of complicated, especially when you need to go to stuff like this, where you convert activators to deactivators. So sometimes they'll throw curveballs like that in, so make sure you know how to convert activators to deactivators and vice versa. Make sense? All right, we've got about 20 more minutes to finish up this chapter. We have a couple more reactions that are thrown into this chapter, I think simply because they don't have another home. And the first one has to do with nucleophilic aromatic substitution. We were previously talking about electrophilic aromatic substitution. This is spinning everything upside down. So I'll show you an example of this. We've got a para-substituted aromatic system with a nitro group para to our bromine. And what we're going to do in step one is we're going to treat this with a strong base or a strong nucleophile. And then step two, we're going to treat it with acid. And when this happens, you can get an alcohol. So you can get para-nitrophenol. So then the question is, well, what in the heck is happening here, right? If we think about hydroxide, that is most definitely not an electrophile, meaning our aromatic ring is not going to attack it. What do you think will happen instead? It attacks the ring, right? So this is a good nucleophile. The other thing I'm noticing is in the title, we're calling it a substitution reaction. In a substitution reaction, oftentimes we have a leaving group. Over here, I've noticed that we've got a bromine. It's a leaving group. Really, this could be any sort of leaving group. So it could be any halogen with the exception of fluorine. It could even be a tosylate or something like that, although it doesn't really make sense to have a tosylate on there. So typically, it's a halogen. So let's take a look at the mechanism. All right, so we're going to start out with our basic starting material. And we're going to consider hydroxide. All right, so my question is, which position on the ring do you think hydroxide is going to attack into? The top one. It makes intuitive sense because that's where the alcohol ends up, right? Second reason, why do you think it's ending up there? Bromine's a good leaving group. And the nitro group is electron withdrawing. If you remember the other day, we said if you have electron withdrawing groups, that means that these positions are delta positive. So in this case, hydroxide's going to attack in right here. It's going to kick off. Oops, sorry. I'm skipping ahead too fast. It's going to attack that carbon. And instead of kicking off bromine, it's going to dump electron density to one of the ortho carbons adjacent to the bromine. So it's not an SN2 reaction. Like we said, you can't do SN2 reactions with halogens coming off of an aromatic ring. All right, actually, I'm going to go ahead and draw out the whole nitro group here. And you'll see why in a second. All right, so we've got this intermediate. This isn't a sigma complex because it's not a cation. Instead, we come up with a new name for it. This is called a Meisenheimer complex. In case you're ever at bar trivia, you can get this right on the trivia question, because I'm sure that's the questions they ask at bar trivia, right? All right, so if we think about this, why is this unusually stable? Resonance. All right, so we can go ahead, dump electrons down here, all the way up to that oxygen. So that electron withdrawing group is actually stabilizing formation of the negative charge on the aromatic ring. There are other resonance structures as well. However, this is the main one. So just like with the sigma complex, we're breaking aromaticity, but it's resonance stabilized when we break that aromaticity, right? All right, so now the question is, well, how are we going to jettison off that bromine? Yep.
Is that resonance one still the Meisenheimer complex, or is there a different name for that now?
So remember, a resonance structure is a hybrid of both of these, right? So it's not one.
Status that you're I wouldn't be surprised.
No, resonance structures are always a hybrid, so you can show them using a variety of structural features. However, really it's a mishmash of both of these that we're seeing. So over here, like I'm showing, that negative charge on one of those oxygens can cascade down and essentially eject off that bromine. You can do it using the other resonance structure too, right? So if you wanted to make it nice and simple, you could just show it like that and show that bromine getting kicked off that way too. It doesn't really matter to me which one you show. I just like showing the resonance so that we're clear that it's stabilized. Yep.
You want us to show both resonance?
Unless I specifically say show all resonance structures, I don't expect you to. Yep. All right, so now when it's all said and done, we have our alcohol hanging off right here, and we've got our nitro group. There's one problem with this though. This reaction you typically have to kind of push along, and in order to push it along, you oftentimes have excess hydroxide used. What do you think happens if we have excess hydroxide around? It'll deprotonate the alcohol. This is an unusually acidic alcohol. Why do you think it's unusually acidic? Oh boy. All right. So if we think about the conjugate base, why is the conjugate base so stable? Resonance, there we go. So it's really, really hard to stop at the neutral species. Usually you overshoot and get the alkoxide, which is why in the next step, we react this with some sort of acid in order to really ensure that this alcohol ends up with a proton off of it at the very end. Does that make sense? So it's a little bit weird. All right, there's a few things that are required in order for this mechanism to occur. You have to spin around 3 times and sprinkle it with fairy dust. Nope. First one is we must have a leaving group. Must be present. Number 2 is that leaving group must be ortho or para to an electron withdrawing group. And then number 3 is that your electron withdrawing group must be very strong. In this example, we used hydroxide as our nucleophile. There's other nucleophiles that will also work. So that's another important thing to remember. You could actually use an alkoxide and make an ether directly that way. You can even use nitrogens with negative charges and have them attack in. They're really good nucleophiles. So it is important to remember that other strong nucleophiles will work as well. Yeah.
Why would this not just do like SN2 substitution instead? Why would it just be a substitution?
Yeah, that's a good question. So does anybody know why we might not observe direct SN2? What was one key requirement for an SN2 in terms of hybridization? Has to be an sp3 hybridized carbon for SN2 to occur, right? If we think about the carbon we're attacking up here, that's sp2, therefore it won't do sp2 SN2 substitution. Sorry, my brain's having a hard time. All right, does that make sense? So down here, we said other strong nucleophiles might also work. Whoops. So you could have something like an alkoxide nucleophile. You could have something like sodium amide as your nucleophile, something like that. As long as it's a really good nucleophile, it can attack in and accomplish this. Yep.
Use like a alkyne.
So alkynes aren't really great nucleophiles. Actually, let me think about that. I'm not sure. I've never seen an alkyne installed in that fashion, simply because there's a lot better ways to install alkynes, but I'm not sure actually. Yeah, normally you do catalytic reactions to install alkynes. You do a reaction called the Sonniger-Scherer reaction, but we're not going to learn about that. Anyways, Sonniger-Scherer reaction. All right, next one is also kind of a reaction that doesn't have a home. This is called elimination addition. It sounds like an oxymoron, but really it means one after the other. So you do elimination first, followed by addition. So let's say we have bromobenzene, and we treat it with hydroxide, followed by acid. Do you think this will do nucleophilic aromatic substitution like we just saw?
No.
Why not?
It says so.
Because it says so. It doesn't have a strong electron withdrawing group in the ortho or para position, so you get no reaction. All right, but chemists aren't satisfied with that, so what do you think a chemist would do if they couldn't get this reaction to work? Just heat on it until it starts boiling, and then wait and wait and wait and wait and wait and wait and see if it eventually will do something interesting. So that's exactly what happened. Chemists did this reaction. And what they did was they treated this with sodium hydroxide, a huge amount of heat, let it run for a long time. At the end, quenched it with acid, and they actually were able to get this to work. The problem with this is it requires really high temps, to the point where it's kind of impractical for most purposes, because you'll end up cooking your compound. This only works for really simple aromatic molecules. Anything that's highly functionalized will essentially decompose on you. All right, so then chemists got interested and they wanted to know how much further they could push this. And so they did the same reaction with a different nucleophile. This one they did with a stronger nucleophile, which is NaNH2. So if you remember, we use this as a base. However, it's also a pretty good nucleophile. And we require a liquid solvent for this, so normally it's ammonia for this reaction. And they could actually get the NH2 group to install. And this works at moderate temps. So chemists thought this was pretty cool. They're like, well, now we can make an aniline directly in one step versus installing a nitro group and reducing it. Pretty interesting stuff. They got curious, though, about the mechanism, because this doesn't have that strong electron withdrawing group. So a lot of people thought this shouldn't work. So there was this famous study done. And I'll show you the study by showing you the mechanism at the same time. All right, and in this study, instead of using an electron withdrawing group, para or ortho to the bromine, they just had some sort of placeholder group, in this case, a CH3 group. And then in the first step, they're going to treat this with sodium amide, which is that negatively charged nitrogen. All right, we know it's not going to do the same mechanism as before. In fact, I gave you a big hint in the title. It's elimination followed by addition. So in an elimination reaction, what happens? You abstract a hydrogen and make a new pi bond, right? So now the question is, well, how is that going to occur? Well, we've got a hydrogen coming off the aromatic ring. You can actually pluck this off and do a pseudo E2 reaction and kick off your bromine. They don't need to be anticoplanar in this place. All right? So that's the elimination portion. So let's make a note here. All right? When they proposed this, people were like, what in the heck are you trying to draw right now? This is called a benzyne. Because it's part benzene and it's part alkyne. People looked at this and they said, wait a minute. Those are supposed to be sp hybridized. They're supposed to be 180 degree angles. People like lost it when they showed this paper. However, his data kind of backed up this idea, and I'll show you some other experiments he did later. So in the next step, we have more amide floating around. So this has the option of attacking right here and kicking electrons up. Or it doesn't really have a strong preference on which side of the alkyne it'll attack. It could theoretically attack this carbon too, right? So either pathway could occur. Whoops, forgot my NH2 group there. All right, so we're almost there. Very last step is we need to make sure we get our neutral product, and that's where the ammonia comes in. Oops. And what he noticed was that the nitrogen didn't care which carbon the attack occurred at, and that was partially evidence for formation of the benzyne intermediate. Does anybody know a way they solidified this and made it kind of common theory? Does anybody know what benzyne might do? Give you a hint. Benzyne is a really, really, really good dienophile. Yeah, so they're actually able to trap that benzyne intermediate by having it do a Diels-Alder reaction. So pretty interesting stuff at this point. But it is kind of weird. Unlike nucleophilic aromatic substitution, which exclusively occurs at one carbon, this will occur potentially at two different sites, so we do have to be careful with this one. Does that make sense? All right, so essentially that's the end of the chapter. If you remember, yeah.
How would you favor one product over the other?
Yeah, so that's a good question. You can't favor one product over the other. It was just kind of an interesting experimental observation. It's, like I said, it's one of these reactions that doesn't really have a home. And they were trying to figure out the mechanism, and this was the best mechanism they could come up with. To be honest, this benzyne intermediate is still debated. There are a lot of people saying it's not a true alkyne. Instead, it's more of a diradical. It's kind of tomato-tomato at that point. You're just arguing semantics, so most people still refer to it as benzyne. Remember, too, to do your sapling. At the end of the notebook for this chapter, I've got all the reaction summaries in OneNote, along with some flowcharts. And then at the very end, I've got the fill-in-the-blank study guide if you want to just print this out and kind of fill in reagents on your own. But make sure you do study. Next Wednesday, we won't have class, but what I will do is give you a synthesis worksheet for this chapter. But I kind of wanted to give you the weekend and a couple days for all of this to digest. Yep.